Right, and without any delay, I'd like to introduce you to Joshua from Cambridge Mechatronics. And I believe Joshua is using shape memory alloy actuators for focus compensation in XR displays. I believe that's what you're going to talk about today. So,
That's brilliant. All right, I'll crack on. Nice to be here and talking today. And yeah, like just mentioned, I'm talking about Cambridge Mechatronics' shape memory alloy actuators. So first, a little bit of a overview of Cambridge Mechatronics. So we're the world leader in the design and the control of shape memory alloy actuators, and I'll come on in my talk to give you a explanation of what SMA, shape memory alloy, is. We use these actuators to enable high-performance miniature actuator systems, and primarily we're shipping our kind of core business today is in the smartphone camera industry. So we use these miniature actuators. You can see a picture on the right-hand side of one of our actuators to do both image stabilisation and autofocus, where we're moving various components to improve the performance of the camera. When you think of Cambridge Mechatronics, we kind of are a full system provider in the sense that we do the mechanical design. We are a fabless semiconductor company, so we provide the driver chips, and critically, we provide the control firmware, which determines the control of the actuator itself. We work globally, so we license our technology to manufacturing partners, predominantly in Asia, who will go on and manufacture the actuators and launch those into end products. So far, actually, we've already had a lot of success in the smartphone camera industry. We've shipped more than 50 million actuators now, starting our kind of big success was 2019 when we made it into the Huawei P30 Pro. And then since then, we've shipped in several high-end phones every single year since then, getting us up to our 50 million units. And now we're really starting to look at new industries, new applications for actuators, and XR displays is one that's really exciting for us. So SMA, what's it used for? It has some really cool applications that other companies are putting this fantastic material to use. One of which is the Mars rover tires. So in this case, the material, which is an alloy of nickel and titanium, is being used for its super elastic property. And in this case, it can undergo a very large strain and then recover its original shape without being damaged. And obviously, on Mars, where there's no atmosphere, having a pneumatic tire susceptible to punctures would be a very bad idea. And so that's a really quite a niche use case. But I have recently seen a company bringing a bike tire with SMA to market, hopefully later this year. And then in the medical world, stents also often using nitinol, which is the particular alloy that we also use, this nickel titanium blend, again for the super elastic property. So I mentioned this super elastic property. Actually, CML is using something slightly different, which is called the shape memory effect, which is where the material can deform through relatively large strains, but then recover its original shape when it goes through, is reheated. And it does that by going through a phase transformation. So in its hot state, the material has an austenitic structure, which is cubic, and generally that's the compact state. When the material cools down, it transitions its phase into a martensitic phase. And in this phase, it can undergo relatively large strains. And so if you load it with a force, you'll see that strain. And then you can recover the original shape by heating it up when it recovers back to the austenitic phase. So some of the key properties of the material itself that we're using are the strain that it can go through. So we use the material in the form of very thin wire, and we can take that wire and we can achieve strain of between maybe 2 and 3%. So that means if you have a 10mm long wire, you can get perhaps 200 microns to 300 microns of stroke from the wire itself. Because the material is going through a phase transformation, it's similar to water changing to ice. And if you've ever put a bottle of water in the freezer slightly too full, you appreciate the amount of force generated when materials go through a phase change when it cracks the bottle. It generates a really high force. So from a very thin wire, we can generate several grams, more than 10 grams of force. And so that means that we can move these heavy components, heavy lenses, heavy displays in these types of systems. And two other key advantages are silent actuation. So going through the phase change is silent, so no noise created, which is critical for when we're looking at putting these in headsets, and the lightweight nature. The material, because we're using such a small volume of it, itself is very light, and then the actuators that go around those can really be very lightweight as well. So what Cambridge Mechatronics has done, we've taken this amazing material and we've understood how to control it. And we do this kind of in two steps. So the first step is that we always have an opposing wire configuration. And so we have one wire which will be antagonistic to a second. And then we can very precisely control the amount of energy going into that wire by passing a current through it. So with a PWM drive, with a low voltage over the wire, you can control the current and therefore the heating of the wire. The voltages that we use are typical consumer electronics, 2.8 or 3.2 volts is very normal. And then we can use the resistance of the wire actually as a feedback mechanism to be able to precisely position components. So lots of people use SMA in a bi-state or a dumb mode where it's not being controlled, but we're using the great properties. But CML has a closed loop feedback system. So the resistance is proportional to the length and inversely proportional to the area, meaning that a cold wire, which is long, is high resistance, and a short fat wire is low resistance. So hopefully this comes across okay on the video link. There's a little clip here of a thermal capture of one of our actuators in motion. So this is a two-dimensional actuator which can do an X and a Y motion. And the nice thing about this thermal capture is that you can see when the wire is heating up, it contracts and is pulling the moving portion in that direction. So it's a nice illustration of how an SMA actuator is working. And to give you a quick appreciation of the kind of precision that we can achieve with these actuators, on the right-hand side, you can see a plot that we've captured with a similar actuator to this, showing a half micron step with approximately 100 nanometers of stability. And so that's the blue line that you can see. And the black line is the measurement noise. So just of our test system, if we were to look at the measurement noise, you can see there's already some jitter in that. And so this kind of precision lends itself to several different applications. But one, which is not actually the main topic of the talk, but is interesting to us, is using these kind of motions for super resolution or for wobulation, so to enhance the resolution of a display system. So one of the great things about SMA actuators is the flexibility of the design that you can do with them. So really it depends on what you need to move, how far you need to move it, what the space available is, and how much power can be used. And then the design can be adapted in so many different ways to be able to achieve that specification. So for example, we can alter the thickness of the wire to change the amount of force that we have available, or you can adjust the length of the wire or the mechanical gain of the actuator to be able to adjust the motion. So for example, the exploded view here is a autofocus actuator, which has a bearing system, which means that we can take maybe 200 microns of stroke from the wire, and cause the motion of the lens, which is doing the focusing, to move through 600 microns because there is a 3 times mechanical gain. And then later on in the design process, the technology is very suitable to high volume manufacture, so we can support the design for manufacture and the cost down to make this acceptable for consumer electronics in high volume. This video is of one of our newer technologies, which has just recently gone into mass production and is shipping in high volume now. And it's really exciting because we use a single actuator here to deliver all 6 degrees of freedom. So you can see in the video, we have a focusing motion, which is the motion along the optical axis. And then you can also achieve a translational motion perpendicular to the optical axis. And in addition to this, this structure with the 8 wires, a cross of wire on each of the 4 sides, also allows you to do roll, so rotation, roll, and the 2 tilts as well. So it's a extremely flexible design. One of the things that we're really excited about for the XR industry is a technology that we're calling zero hold power. And what this means is that we can use the high force available from the actuator to come up with structures where you only need to apply power to move to a new position. And so what this means is for periodic uh, position adjustment or focus correction, you can have a very low average power consumption. So as an example, a typical OIS power consumption or autofocus power consumption might be 100 or 150 milliwatts, and it always requires power. But with these new configurations, if you're only doing one on motion per minute, so perhaps you're just adjusting the focus once per minute to just make sure that you're in exactly the right position. Now the average power consumption drops dramatically because you just have a deep sleep of the chip and no actuator power consumption to hold the position, and just a small amount of power when you need to move to a new position. So something less than 1 milliwatt for one motion per minute is extremely achievable. So what are some of the applications of this zero hold power technology? I have 2 for you today. The first is focused more on display systems for virtual reality, which is a varifocal system. And this is obviously at the larger end of the spectrum. So here we'd be looking at moving a lens or perhaps the display relative to each other to adjust the virtual image distance to match that to the stereoscopic distance and reduce that divergence accommodation conflict. And if you look at the headsets that are shipping in the market today, or approximately what the Vision Pro is expected to require, you're looking at doing motions of perhaps between 1 and 5 millimeters, and with the kind of precisions that we're regularly doing. And it's a very achievable type of actuator for this technology. Another example, and I think this applies to both virtual and augmented reality, is thermal compensation. So as the temperature changes and the thermal load in these headsets is very difficult to manage, the optics will adjust their shape slightly, causing the focus position to change. And you could use this actuator technology to intermittently correct the position you turn on, you measure the temperature, you move to the new position, you turn off again. And it allows you to use the highest quality optics without compromising on the power consumption or the size. Just lastly, I wanted to talk about a couple of the other applications of actuators in AR and VR vision systems. So I mentioned briefly wobulation, but as well as that, there's also a use case for dead pixel mitigation, where you're shifting by pixels and compensating for a lack of a pixel or even pixel to pixel variation. and potentially even something like prescription correction. Again, that accommodation correction is another application. And of course, all of the same stuff that we've been doing for the smartphone camera industry, all of the camera technology could also be adapted into the XR headsets as they advance into new products and new generations. So I'm gonna wrap up talking there now, but really welcome any questions that there are from the audience, and if there are any follow-ups afterwards, this is my contact details, and please feel free to reach out.
Joshua, thank you. That was really appreciate that. Good talk. Good talk. Um, Joshua, I've got a question for you, and I love the background there. I've been to Cambridge many a times, a beautiful city. Um, and forgive me if I missed this, but over what range of temperature do the SMA actuators work? And can you give an example of how fast SMA actuators can be?
Yeah, sure. So the the range temperature, we're basically good for consumer electronic specifications. So we often spec from -30 degrees Celsius up to perhaps 65 degrees Celsius,
Mhm.
which for almost all applications we've seen shipped in so far is acceptable. One thing you can do is you can tweak the composition of the alloy. So if a higher temperature is needed, we can tweak the alloy, and that would allow us to hit higher temperatures. And then in terms of the speed of motion, I can give you two examples. So firstly, for that wobulation type motion, we'd be looking at doing steps of a couple of microns in perhaps as quick as a millisecond or a couple of milliseconds. And then for an autofocus actuator, maybe for a median transition of 30 microns, you'd be looking at perhaps 10 or 15 milliseconds.
Okay. All right. I'm just waiting to see if there's any questions that come through the audience here. If you do have questions, please type them in. Don't be shy. We'll just give it a few minutes because the way it's working for me, Joshua, is I can't actually see their questions for some reason. So some of my colleagues are feeding them through to me on my phone. So we'll give it a few seconds here to see if anybody has any questions. And if you do, again, please don't be shy. That's what Joshua is here for, and I'm sure he'd be happy to
Yeah.
answer any questions you might have.
Yeah, of course, no problem.
Well, it appears they are being shy, Joshua, and I think that's what it was. So,
Well,
or you were just
they've got my contact details, so anyone's welcome to
yeah.
reach out if they do have any questions coming up.
Uh, okay, great. It may be because you gave such a good presentation that you just covered all the questions too. So, yeah, enjoy the day in Cambridge. I'm in Hertfordshire myself, so we're not getting the best weather at this point in time, but enjoy the rest of the day, and thanks for joining us, and thank you for the presentation.
Yep, thanks, you too.